Pluto is a far-off and puzzling midget planet, which was once an individual from our nearby planet group's planetary family. However, recent alarming declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning disclosure. They recommend that this cold world is on a potential crash course with Neptune. But how could this happen, and what might be the results of such a monstrous event? Are we seeing an interesting cosmic peculiarity, or is there something else to this approaching enormous crash? Join us as we investigate the possibilities of a Pluto-Neptune influence. Pluto, a former planet that was downgraded to a dwarf planet mostly due to its exceptional orbit, remains a subject of interest and study in the galactic community. As indicated by recent forecasts by leading researchers, Pluto's orbit is dangerously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential perilous crash between these two planets, which could pose a gigantic threat to Earth. But how is such an event even conceivable? Pluto's journey around the Sun is unlike any other planet in our solar system. It requires a stunning 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full revolution. Yet, the interest doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its inclination, calculated at 17 degrees to the ecliptic plane. The path Pluto follows is much more steep compared to the other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, contradicting what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to figure out its peculiar path. Unlike the other planets, whose orbits lie somewhat near the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit, amidst these complexities, is proof of the intricacies of space mechanics. The three-body problem in space deals with determining how three objects in space, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on one another. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all cooperate in a complex manner. The terms azimuthal libration and scope libration, along with the VZK oscillation, are essential parts of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is azimuthal libration. In the case of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is situated at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from intersecting. Scope libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned well above their orbital plane, providing an extra layer of protection from potential collisions. Another key part of this situation is the VZK oscillation. This is named after three researchers, Bond, Zippel, and F, who studied how objects move in space. It's about how three space objects, like Pluto, Neptune, and the Sun, pull on one another with their gravity. This pulling influences how they move. In Pluto's case, the VZK helps us understand why its orbit around the Sun is so unusual. Even though Pluto's path seems chaotic, this oscillation helps keep it moving smoothly from here onward for millions of years. The VZK oscillation shows that even when things in space seem wild and random, some patterns and rules keep everything together. All of these factors help keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or veer off course. This three-body problem helps us understand how these parts change based on how these space objects pull on one another. Studying this helps us learn more about Pluto, our solar system, and distant worlds and their stars. Mathematical simulations in the late 1980s revealed that, despite these stable properties, Pluto's orbit is actually turbulent, with minor deviations in starting conditions leading to significant differences over thousands of years. However, these special properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, still keeping the chaos under control. Recent computer simulations have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's path around the Sun. Neptune has a unique relationship with Pluto, wherefore, every 2 orbits Pluto makes around the Sun, Neptune makes 3. This relationship helps keep Pluto's path consistent. But Neptune isn't the only one helping. Jupiter's gravity also plays a major role in safeguarding Pluto's orbit. In fact, Jupiter's gravity alone is powerful enough to ensure Pluto stays on a stable path for a really long time, even billions of years. So, it seems like Neptune, Jupiter, and Saturn are working together to make sure Pluto continues to move safely in space without running into trouble. These peculiarities are crucial in the broader context of the universe, helping maintain the order and consistency of celestial bodies' movements. Without these mechanisms, our solar system would be a much more chaotic and unpredictable place. Bodies like Pluto could potentially crash into others or be ejected from their stable orbits, leading to a domino effect on other celestial bodies. For Pluto, especially with talks about it potentially colliding with Neptune in the future, understanding its orbit is very important. It gives us a clearer picture of the solar system's dynamic nature. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve a state of balance through the complex interplay of gravitational forces and orbital mechanics. It also shows the importance of continuous observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often leads us to confront the erratic nature of celestial bodies, and Pluto's orbit is a perfect representation of this unpredictability. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's path on its initial conditions, is strikingly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can drastically change its long-term orbit. Using virtual simulations has been incredibly helpful for scientists to figure out how Pluto moves in space. These simulations use sophisticated math to model how Pluto and other space objects, like Neptune, pull on one another. By changing tiny details in the simulations, astronomers can see how even small changes can make a huge difference in where Pluto ends up. In the late 1980s, these simulations revealed something really interesting about Pluto's orbit. Even though it has things like azimuthal and scope libration to keep it stable, its path can still be wild and erratic if you start with just a tiny difference in where Pluto is or how fast it's moving. Over many years, its path can end up looking really different. But even with this chaos, Pluto's orbit remains stable for a long time, like billions of years. This means Pluto's journey around the Sun has some sort of order to it, even though it might seem all over the place at first. Predicting infinite events, especially when they involve turbulent orbits like Pluto's, presents significant challenges. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While mathematical simulations provide a powerful means to understand and predict the future behavior of celestial bodies, they also highlight the limitations of our predictive abilities. These models rely heavily on the accuracy of starting conditions and the complexity of the interactions they simulate. Any slight mistake or misrepresentation can lead to vastly different results, making precise predictions a daunting task. Moreover, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we've made great strides in understanding space, the case of Pluto serves as a reminder of how our knowledge of the universe is still limited. Understanding the gravitational effects of the giant planets on Pluto's orbit gives valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have significant impacts on the stability and trajectory of other bodies within the system. So why are major astrophysicists only now raising concerns about a potential crash between Pluto and Neptune, despite all these complex forces working to prevent such an event? Neil deGrasse Tyson, a prominent astrophysicist and a key figure in popularizing cosmology, offers a unique perspective on the mysteries of our solar system, especially the fascinating case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, provides insightful discourse on the evolving nature of celestial mechanics and the public's fascination with the unknown realms of space. Tyson's position on Pluto's renaming is rooted in the ever-expanding knowledge of our solar system. He views the renaming not as a downgrade, but as an important adjustment to our growing understanding of the many bodies orbiting our sun. His approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits, like Pluto's, as a sign of how much more there is to discover in space. The interest in these questions, particularly the possible interactions between Pluto and Neptune, highlights the dynamic and often unpredictable nature of our solar system. His work emphasizes that the more we uncover about space, the more questions arise, pushing us to explore further and refine our understanding of the universe. Michio Kaku, another renowned physicist and futurist, offers a different yet complementary perspective on the mysteries of space, focusing on the often unpredictable forces that shape our universe. Kaku is known for his ability to connect complex scientific concepts with cutting-edge visions, making him a significant voice in discussions about celestial mechanics and the broader implications for humanity. Kaku's views on Pluto and its orbit underscore the need for continuous observation and advanced modeling to predict and understand potential cosmic events. He sees the interactions between celestial bodies as a critical area of study, not only for academic interest but for practical implications. The potential impact between Pluto and Neptune, for example, is not just a hypothetical scenario but a reminder of the dynamic and often chaotic nature of space. Kaku's futurist perspective urges us to consider the broader implications of such events, from the impact on our understanding of the solar system to the possible need for future space interventions. Kaku's viewpoint highlights the importance of being prepared for the unexpected in space. His work suggests that the more we understand the forces at play, the better equipped we will be to navigate and potentially mitigate the effects of cosmic events. Both Tyson and Kaku's perspectives converge on the idea that space is a realm of endless discovery and that our current understanding, while vast, is still limited. Their emphasis on the need for continuous exploration and advanced modeling reflects the evolving nature of space science. They highlight the importance of not only understanding celestial mechanics as they are now, but also speculating on how they might change in the future. The potential crash between Pluto and Neptune serves as a case study for the broader challenges and opportunities in space exploration. It underscores the need for rigorous scientific inquiry, cutting-edge technology, and a willingness to adapt our understanding as new information emerges. For Tyson and Kaku, the mysteries of space, exemplified by Pluto's orbit, are a call to action for the scientific community and humanity at large to keep pushing the boundaries of our knowledge. There is a general scientific consensus that for many years to come, the orbits of Pluto and Neptune will remain stable due to their mean motion resonance and the various gravitational influences acting on them. Therefore, a direct crash between Pluto and Neptune is highly unlikely. However, the complexities and potential perturbations in orbital elements mean astronomers must continue to monitor and study these celestial bodies to better understand their long-term behavior and any potential risks they might pose. While the possibility of a Pluto-Neptune impact remains largely theoretical and considered unlikely with our current understanding, it highlights the importance of ongoing exploration and observation in space science. Advances in technology, including improved telescopes and computer simulations, will help astronomers refine their models and predictions, ensuring we stay abreast of the dynamic and ever-changing nature of our solar system. Tyson's perspective on Pluto's renaming and Kaku's emphasis on the unpredictable nature of celestial mechanics both highlight the need for continuous investigation and an adaptable understanding of our universe. The potential crash scenario, while illustrating the dynamic and complex interactions within our solar system, ultimately reminds us of the vast, still unknown territories in our comprehension of space. Through ongoing research and observation, we strive to unravel these mysteries, ensuring that our knowledge keeps pace with the ever-advancing universe.